In this exercise, we will look at the AB class of distributions, which is the class of distributions that we can use to model the claim numbers when we wish to use the Panzer recursion to find the total claim amount. So read a bit more on section 333 if you are in doubt about what the Panzer recursion is. The thing that we will show in this exercise is that there are in particular three distributions that satisfy what we call the AB condition that defines the AB class of distributions. And in fact, those three distributions are the only distributions in the AB class of distributions. So we say that a discrete probability distribution satisfies the AB condition if its point probabilities can be written on the form qk equal to a plus b divided by k multiplied by qk minus 1 for some a or b in the reals and for every natural k. What we mean by this is that for a discrete probability distribution, we will start in Q0, which denotes the probability that a variable with this distribution attains the value 0. Then using Q0, we can use it to find Q1. So we can find the probability that n is equal to 1 by taking a plus b divided by 1 multiplied by Q0. And then we can find Q2 using that. So Q2 by writing a plus b divided by 2 multiplied by Q1 and so on. And this is what we mean by this recurrence relation up here that defines the AB class of distributions. So what will we show in this exercise? Well, in part A of the exercise, we will verify the AB condition for three distributions: for the Poisson distribution, for the binomial distribution, and for the negative binomial distribution. And also we will find what we call the AB regions. So we will find out which A's and B's so which regions A and B should lie in each of these cases. So we will find that as well. So basically what we show in A is that if something is Poisson distributed or binomially distributed or negative binomial distributed, then the AB condition is satisfied. So we will show that Poisson binomial or negative binomial, well, implies that the AB condition is satisfied. Now what we will do in B is to show that outside of these three regions of A's and B's, this recurrence relation does not define any distribution probability. So what we show in B is that if A comma B does not lie inside the AB region for the Poisson distribution, or the AB region for the binomial distribution, or the AB region for the negative binomial distribution, then it implies that QK defined as such cannot be a probability distribution. And lastly, in C, after we have shown this, then we will show that if the AB condition is satisfied for any AB that lies inside this, then it implies that QK must be one of these distributions. So if A or B lies inside, let's just call this set R, well, then QK must be either a Poisson distribution, binomial, or a negative binomial. So essentially in A, we go this way, and in C, we go the other way back. So and there are a lot of subtleties here. We cannot just skip any of the exercises because in fact, we're doing something different in each of them. And I will explain later why A and C are two decidedly very, very different exercises and why C is in fact a lot harder. So the thing that we'll do now, just before we start, is to write up the point probabilities in each of the three cases of distributions. So if we have a Poisson distribution, let's write it like this. So if n is Poisson distributed with parameter lambda, where would that lambda be greater than 0, then it means that n attains the value k with the point probability e to the minus lambda, lambda to the k, divided by k factorial. So this is one of those that, well, it could be nice if you memorize this. And if n is binomially distributed with parameters n and p, where n is some number of independent trials and p is some probability of success, then n attains the value k with probability n choose k multiplied by p to the k when minus p to the n minus k. And just note that in the Poisson case, k belongs to the naturals extended with 0. However, in the binomial case, k is equal to 0, 1, 2, and so on up until n. And then let's also just define the point probabilities in the negative binomial case. So if n is negatively binomially distributed, then we have the parameters v and p, where v is just any positive number and p is some probability parameter. Then the probability that n is equal to k is given by k plus b minus 1 choose k multiplied by p to the v multiplied by 1 minus p to the k. And once again here, we just have that k should belong to the naturals extended with 0. So we have these point probabilities here, and we will use these in just a second. However, I will also do an extra video that you may choose to watch or not to watch about the binomial and negative binomial distributions, about how to interpret them, and some probabilities, some properties that the negative binomial distribution has, since v is just a positive number, and hence we are actually looking at what we call a generalized binomial coefficient here, because the k plus v minus 1 is just any real number, more or less. So that is what we will look at in the next video before we actually start solving the exercise.